going to find all of the angle measures. So since they're giving us all of the angle measures here, we're going to use the triangle sum theorem, and we're going to add the angles to equal 180 degrees. So when we combine like terms, our x term will be 12 once we add 4, 3, and 5. And then 20 minus 8 is 12. So combining like terms will give us this, then subtracting 12. And dividing by 12. So 168, when we divide by 12, we get 14. So I'm just going to write that down. This is how we would set up our division for 168 divided by 12, but we got x equals 14. So they're asking us to find the angle measures, so we're not done once we get x. We need to take x and plug it in to each of these angles. So I'm going to start with this angle here and plug in x equals 14. So 5 times 14 will give me my first angle measure here of 70 degrees. And then I'm going to plug in next here to 4x plus 20. So 4 times 14 plus 20. So 4 times 14 will give us 56, and 56 plus 20 will give us 76 degrees. And then the last angle here, 3 times 14 minus 8. And then 42 minus 8 is 34 degrees. So now that I have each of my angle measures, they're asking me to kind of put them in order. So they want the smallest angle measure. So out of these three, I'm going to put 34 degrees. Then I have my middle angle, 70 degrees, and the largest angle, 76 degrees. Number 2, we're asked which of the following would form a triangle. And we are given 3 angle measures. We remember that in a triangle, the interior angles need to add up to exactly 180 degrees. So if I were to add 33, 67, and 103, that would not give me 180 degrees. So I'm not going to pick the first set. That's 203 degrees when you add them all together. So we know it's not that. Now let's try 45 plus 45 plus 90. If I added those together, that would give me exactly 180 degrees. So I'm going to go ahead and circle that set of numbers. That would work. And then I'm going to add 20 plus 60 plus 110. Adding those numbers together gives me 190 degrees, so that's not going to work. And then lastly, 36 plus 54 plus 80 degrees is 170 degrees, which does not work. So 45 degrees, 45, and 90, those do add to equal 180 degrees. All right, number 3, we are going to be marking the diagram with this given information, and then we're going to talk about which theorem or postulate can be used to prove the triangles are congruent. So before we get into that, I'm going to write down our options. We only learned about 3 different theorems for proving triangles are congruent. We're either going to be using SSS, SAS, or ASA. So starting with this information, MQ is parallel to PN, so I'm showing little arrows to show that these 2 lines are parallel. They're not congruent, so don't mix that up. This is not telling me these sides are congruent, they're parallel. So if you extend these lines, we can see that with this transversal of MN, we're going to have congruent angles. And then also with this transversal QP, we're going to have congruent angles. So that was because of alternate interior angles. So I'm going to keep in mind that these parallel lines gave me some congruent angles, and we'll come back to that. The next piece of given information is that QR is congruent to RP. So that right away is giving me a pair of congruent sides. So for me, I already know we're not using SSS because I only have one pair of congruent sides. We cannot say ASA yet because the side here that is congruent is not between the angles. It's not included. But when we see these triangles that share point R, we have to remember the vertical angles are congruent. So this will give us ASA. We have two pairs of angles and the included side. Okay, so we are using ASA. And then sometimes we like to mark them like this. Angles, all of the pairs of congruent angles, plus the sides. So you see ASA a little clearer. All right, and number 4, we're gonna always mark the given information to answer the question. So in triangle PQR, we have PQ congruent to PR. So I'm making my marks there. Measure of angle P is 70 degrees. And we are going to use that information to find the measure of angle Q and the measure of angle R. So this is our isosceles triangle where when we have two pairs of congruent sides, we know, I should say two congruent sides, then we know we have two congruent angles. And it's the angles that are across from the sides. Okay, so you imagine that tick mark is almost like an arrow that went towards this angle. And then this tick mark went towards this angle. So these are the two congruent angles. Okay, so if those are congruent and I need to solve for them, I'm going to go ahead and call one of them x. So I'll call angle Q x so I can solve. But since I'm calling that x, then R would also need to be x. And I know that those three angle measures inside of the triangle will add to equal 180 degrees. So when I solve this equation, I end up with x equals 55. So that means my angle measure here, angle Q, is 55 degrees, and here angle R is 55 degrees. So something really good we should do on our test to check our answers is remembering that the three angles need to add up to exactly 180. So I'm going to show you that if I wanted to check my work, I could do that really quickly by taking these three angles, adding them together, making sure they equal exactly 180. And in this case, 55 plus 55 plus 70 is 180. So I know that those answers are reasonable and make sense. All right. I should probably write those a little bit clearer actually. Measure of angle Q, 55 degrees. Measure of angle R, 55 degrees. All right. In number 5, we are asked to find the measure of angle 1, measure of angle 2, and the measure of angle 3. So we have 3 different triangles here. And when I look in each of these triangles, I can see that in this triangle on the bottom, I'll highlight it, this is the triangle that's giving me enough information to solve for the missing angle first. So here I have 2 out of the 3 angles in the triangle. So I'm going to call angle 1 x, and I'm going to be able to solve for angle 1 using my triangle sum theorem. Okay, so combining like terms. I end up with x is equal to 80 degrees. So angle 1 right here, I'm going to write in, it's equal to 80 degrees. I know it's kind of small, but all right. So right away, angle 1, 80 degrees. We got that using our triangle sum theorem in this yellow highlighted triangle. Okay, so there's different ways we can move forward now. I'm going to look at finding the measure of angle 2. So if I need to find angle 2, I'm going to call it a different variable. I'll call it y. We don't have enough information. We don't have 2 other angle measures. So what we'll need to do is use this 80 degrees we got down here. And we need to remember that these 2 angles are a linear pair. So if this is 80 degrees, then we know that this has to be 100 degrees because of linear pair. So now I have enough information to solve for y. I have y plus 100 degrees plus 46 degrees equals 180 degrees. So combining like terms, or adding 146 is 146. And then solving here, y is equal to 34 degrees. So that's telling me right here, angle 2 is 34 degrees. Okay, and then lastly, I'm going to come over here to find angle 3. I don't have enough information in here to find angle 3, but I can use vertical angles. If this is 100 degrees, then I know that this angle across from it is 100 degrees. Those are vertical angles, they're congruent. So now I'm going to call angle 3 a different variable. I'll call it r. R plus 44 plus 100 equals 180. So we have the triangle sum theorem again for the third and final time. So combining like terms, we get r equals 36 degrees. So the measure of angle 3 is 36 degrees. So we want to make those answers nice and clear. Okay, number 6, triangle ABE was rotated 180 degrees around E to form triangle CDE. So with that, we're going to state all of the pairs of congruent segments and angles. We know that there's 3 congruent segments and then 3 congruent angles. We're going to have to name all of those. All right. So if ABE is rotated around to CDE, we can see that angle A and angle C are going to be the congruent parts. So right here, I'm going to write that angle A is going to be congruent to angle C. Okay, then we can see angle B right here. That's going to rotate around to land on angle D. And then lastly, this angle here will land over here. But we want to be careful not to say angle E is congruent to angle E because there's too many angles happening here. We're going to use 3 letters. So angle BEA is congruent to angle CED. Okay, so looking at the order of the letters kind of helps you out. So angle A, or A needs to land on C, so those angles must be congruent. The second letter B must land on D, so that helps you to see those parts need to be congruent. And lastly, E lands on E, but we can't, remember we had to improvise there with stating the 3 points to name the angle. All right, so we have our 3 congruent angles. Now we're going to look at our 3 pairs of congruent sides. When we rotate this one around, BE is going to land on ED. So you can look at the number of arcs to help you out with that. 3 and 2 arcs, 3 and 2 arcs forming here. So I'm going to write down that BE is congruent to ED. Then I'm going to jump over to this side length, AB, and I'm looking at the arcs to help me over here between 1 and 2 arcs, between 1 and 2 arcs. So AB must be congruent to CD. And then lastly, side AE is going to land over here on CE. And looking at those markings helped us see that. So AE congruent to EC. All right, in number 7, we have our isosceles triangle again, where we have the congruent sides, 2 congruent sides, where we're going to have these base angles that are congruent. Okay, so here, if I want to find x, I'm understanding that these are congruent angles, so we're going to set those equal to each other to solve for x. So keeping in mind that that 32 length that they're giving us for the side is not necessarily needed. We don't use that. We set these angles equal to each other, and then we're able to solve for x. So x equals 5. And again, if you wanted to check your work, you could plug in 5 right here. 25 plus 25. Oh, then I made a mistake. Let's see. Whoops, do you guys see that? I'm glad I thought of plugging it in because I made a quick little mistake. It's supposed to be 15 divided by 5 is 3. That was my fault. Okay, so plugging in 3, 5 times 3 is 15. 15 plus 25 is 40. So you know you solve for x correctly. All right, using this diagram below, we're going to write an equation that can be used to solve for x, and then we're going to give a reason. So when I look here, I can see that I have 3 angles inside of the triangle, the interior angles. We know that those 3 angles are going to add to equal 180 degrees. And the order we're adding those doesn't matter. Okay, so each of these angles add to exactly 180 degrees. So that's one equation. My reason is the triangle sum theorem. Okay, those angles add to equal 180 degrees. Another equation that can be used to solve for x would be, if we go back to Unit 1, we learned about a linear pair. So what I just circled in pink, you can see that those 2 angles are forming this line. They're a linear pair, so we add them to equal 180 degrees. And my reason here, linear pairs are supplementary. Whoops, running out of space. Okay, so now that I have my 2 different equations, I can choose either one to help me solve for x. So I'm going to use this little bit of a shorter equation here, my linear pair equation. So I'm going to combine like terms. 8x and 2x is 10x. Negative 36 and negative 24. I'm going to add those together, negative 70. Ooh, I meant 60. Add 60, divide by 10. So x equals 24. And then we're going to find the measure of the exterior angle. And we're going to do that by understanding that, let me get a different color. This orange angle is the exterior angle, okay? We'll make a note of that. That's the exterior angle, the angle on the outside of the triangle. So we're going to take x equals 24 and we're going to plug it in right there for x. So using that expression for the exterior angle, we're going to plug in x equals 24. So when we multiply, get 192, and then 192 minus 36 is 156 degrees, and we have our exterior angle. Okay. Next problem here is our 2-column proof, where we are going to be using the given information to prove that the triangles are congruent. So we will start with writing the given information. XY is parallel to ZA will be my first given statement. And then as I'm writing these down, I need to make sure that I mark up the picture. So XY is parallel to ZA. I'm keeping in mind that these mean parallel. They do not mean congruent. And when we have these triangles with parallel lines, we're going to keep a lookout for alternate interior angles. Okay, so we'll come back to that. All right, we're going to mark that YB is congruent to BZ. I'm going to go ahead and put an S here because right away I know I have a pair of congruent sides. That'll help me with proving. So YB is congruent to BZ, and that's given. Okay, and then again, we already have one pair of sides. Okay, so with this pair of sides, I'm going to look at these parallel lines. Because of these lines being parallel, I am going to have that this angle Y is congruent to angle Z because of alternate interior angles due to the parallel lines. So angle Y is congruent to angle Z. This is because alternate interior angles are congruent. So now I have a pair of angles that we know are congruent thanks to our parallel lines. And then I'm looking at this picture and I need to figure out one more congruent part because I need 3 congruent statements in order to prove the triangles are congruent. So there's no other given information to help me unless I say these angles are congruent, but that would not help me because it doesn't include the side. So again, whenever we see these triangles that share the same point, we are going to have vertical angles. Okay, so I have another pair of angles that are congruent. This angle right here, we can't call angle B, we're going to call angle XBY, is congruent to angle ZBA. Okay, and that's because they are vertical angles, and vertical angles are congruent. Okay, so I stated another pair of angles. But now, since I stated 3 pairs of congruent parts, these work for angle side angle, we are ready to say that triangle XYB, from here, right, XYB, is congruent to triangle AZB, and this is by our angle side angle congruence theorem, ASA. We helped figure that out by marking the diagram and stating the letter A for the angle and S for the side. You saw 2 pairs of congruent angles and 1 pair of sides, so we knew we were using ASA. And number 10, we are given a pair of congruent sides, so we're going to mark them. TU is congruent to TV, and the measure of angle B is 40 degrees. With that, we're going to find the measure of angle T. So I'm going to need to remember that 2 congruent sides means we're going to have 2 congruent angles, okay, so from our base angle theorem. So I'm understanding that this angle opposite and this angle opposite, those are congruent. So if this is 40 degrees, then this angle U is also 40 degrees. So if I want to find the measure of angle T, I'm just going to put an X, and I'm going to use my triangle sum theorem, where these 3 angles add to equal exactly 180. So that angle T is equal to 180, not 180, 100 degrees. Number 11, we're going to state the third congruent statement needed in order to prove triangle DEF is congruent to triangle ABC using our ASA congruence. So far they're giving us DF is congruent to AC. So we have a pair of sides. You can also mark them down here if you'd like. Then we have angle F is congruent to angle C. So we have a pair of congruent angles. And then we need to figure out what is the third part that should be congruent for ASA. So remember, ASA means you have 2 congruent angles and the included side. So this side right here needs to be included between the angles. So highlighting might help us see that on this part of the segment, we need a congruent angle. And then on this part, of the segment, we need a congruent angle. So we would have to say that angle D is congruent to angle A. That would give us ASA congruence. All right, number 12, we are going to answer the two questions and we're going to be as specific as possible. So we're going to describe a single transformation that maps triangle JKL, so that's this one here, onto triangle JK prime L prime. And then that's showing that these two are congruent if we can state the single transformation using rigid motion. So we can see that J needs to land on J prime, K needs to land on K prime, and L on L prime. So this is a reflection across the x-axis. Okay, so you not only need to say that it's a reflection, but you have to specifically tell us what we're reflecting over. Okay, so this is over the x-axis. Then we're going to describe a single transformation that maps triangle JKL onto J double prime, K double prime, L double prime. Okay, so from this triangle to this triangle, we understand J needs to map onto J double prime, K onto K double prime, and L onto L double prime. So counting from J to J double prime, we're going to see that this is just slid across. It's not turned, it's not flipped. So we know that this is a translation, but we have to be specific. So I'm going to count that this is 6 units left and then 1 unit down for those vertices to align. So we're going to specifically write that. This is a translation, 6 units left and 1 unit down. Just as a heads up, we in Unit 2 used a lot of this coordinate notation. If you'd like to use that to describe, you can. We would say x minus 6 and y minus 1. That's just another way you can say it using the symbols instead of words. Number 13, we're going to look at the pair of triangles below, and then it's asking us to find the transformations that are incorrectly stated. So, is this a correct example of a reflection? The answer is no, because if I were reflecting, it looks like they would want to reflect across this line. The congruent parts do not match. So 1 tick mark is supposed to land on 1 tick mark. Okay, and that doesn't happen if you reflect. Here, this is a rotation, yes, because these triangles are turned to land on one another. Is this a correct example of a translation? Yes, this would just be slid across the paper. And then lastly, is this an example of a reflection? It looks like we would have to use like maybe a line like this, but no, it does not work because you can see that if we reflected, the 1 tick mark here would land on the 2 tick marks, and that's not what we want. We need the congruent parts to land on one another. Okay, so you can see that this triangle is actually slid across the paper, so the correct answer would be a translation. So, okay. We have triangle GHJ and triangle JKG are congruent by side, side, side. Okay, so that's good. With that, we're going to list which of the following rigid transformations maps one of these triangles onto the other. All right, so if we look at these sides, if you kind of mark up, we have our reflexive property that shows us that JG is congruent to JG. We're going to have JH congruent to GK, and then JK congruent to HG. And I'm looking at the order of the letters to help me out with that. Or I can look at H and K, second letters. Those need to land on one another. If you were to rotate around J, you would see that this triangle could land over here, but it wouldn't be an exact match. But if you translate it, that just means we're moving it up or down. That doesn't happen. But rotating is what's happening. Okay, so we are rotating about the midpoint. I'll show you guys the midpoint of JG. The midpoint is right there. So you imagine if this top triangle was rotated around this point, it would land down here exactly on the congruent parts where it's supposed to be. We're going to choose which of these transformations map triangle ABC onto triangle RST. So it's important that we read that. We're trying to move from ABC to RST. So make sure you don't go backwards to prove that the triangles are congruent. All right, so if we look to see if this is a reflection across the y-axis, it is not, even though it looks like it, maybe because of point B and point S. But if you look down here at R, 2 units away from the axis, and then C, 3 units away, that is very clear that it is not a reflection. But also, you don't want the angle A to map onto, or I'm sorry, you don't want angle C to map onto angle R, right? You want C to map onto T. So that tells you that this is supposed to be a rotation of some sort. Okay, so it's not a reflection. It's not a reflection. So I'm eliminating A and C. Plus x equals 2 is this line over here. Definitely not reflecting across that. Okay, so we're looking at going from triangle ABC and going toward or mapping onto triangle RST. So 90 degrees counterclockwise will be our answer because we do want to move one quadrant to the right, and you can see that you get your right angle or 90 degree angle formed with this origin here. So it is a 90 degrees counterclockwise rotation, which is the same thing as a 270 degree clockwise rotation, moving all the way around 3 quadrants here. And number 16, we're given information with the blank triangles. As always, we're going to go in and mark up our triangles. So BD is congruent to BC. So we have a pair of congruent sides. Then angle D is congruent to angle C. So we have a pair of angles. Okay, and I kind of like to mark it up here as well. So which one of these congruence theorems is going to tell us that the 2 triangles are congruent? So far I only have 1 pair of sides and 1 pair of angles, so I know it's not this. You have to be able to look at these 2 triangles sharing point B and know that by vertical angles, angle ABD is congruent to angle CBE. So we're using ASA. Okay, to give a little explanation, I'm going to show on here that I was given a pair of congruent angles. I found that angle ABD is congruent to angle CBE because vertical angles are congruent. So I so far have 2 pairs of angles, and then I knew that I was also given the included sides are congruent. And because of this, the triangles are congruent by angle side angle, or ASA. For number 17, given these 2 triangles with the given information of some lengths and an angle measure, we're going to look at each of these people with their, understanding of what they see in the triangle, and we're going to determine in detail who is correct and who is incorrect. So John says that these 2 triangles are congruent according to the SFHS criterion for triangle congruence. Remember, SFHS means we have 3 pairs of congruent sides. But if you look here, we have only 2 pairs of congruent sides. There's not the third side here. So John is incorrect. John is incorrect because there are only 2 pairs of congruent sides. Okay, and we understand that for SSS, we need 3 pairs of congruent sides. All right, Paul. Paul says that the triangles are congruent according to side angle side criterion for triangle congruence. So if you look at these triangles, we do see that we have 2 pairs of sides. I'm going to go to mark those up. And we have an angle, but that is not an included angle. Okay, so Paul is not correct because the angle is not included between the pairs of congruent sides. Okay. And then George says the triangles are congruent by angle side angle criterion. And we're going to say no because we only, again, have 1 pair of angles and 2 sides, so that would not work. So we'll say George is incorrect because there is only 1 pair of congruent angles. For ASA, you would need 2 pairs of included angles with the included sides. Lastly, Ringo says they're congruent according to SSA, and I'm just going to say SSA is not a congruence theorem. Okay, so that is why Ringo is incorrect. That is not a thing, Ringo. And I spelled theorem wrong. Okay, for number 18, we're going to write the equation of the line passing through this point, negative 1, 8, and parallel to the line y equals negative 5x plus 1. So when they're giving us a point and the slope, we know to use our point slope formula, where we will be plugging in x1, y1, and because we're writing the equation of the line parallel, we know parallel lines have the same slope, so we will be using negative 5 for our slope. So we have y minus 8 when we plug in y1 equal to my slope of negative 5, and then x plus 1. And we want slope-intercept form. So distribute here, and then isolate y by moving over that 8. So y equals negative 5x plus 3. That's some more review from Unit 3. Then we're going to write the equation of the line passing through the point negative 5, negative 6, and perpendicular to this line. So I'm just going to write in that we know perpendicular lines have slopes that are opposite reciprocals. So when I look at the slope here of 1/2, we are not going to use 1/2 in our formula. We're going to use the opposite reciprocal. So we're going to use negative 2 over 1, which is the same thing as just saying negative 2. Okay, so that's what we're going to use for our slope. So I took this slope, change the sign, flip the fraction, because we want the perpendicular line. So here's my formula again. Plugging in x1, y1, and then plugging in the slope of -2. And then I'm going to write this in slope-intercept form, so I'm distributing -2, and then isolating y. So y equals -2x minus 16. Number 20, we're looking at FG with endpoints here. We're going to find the slope of the line parallel to FG. So I'm going to use my slope formula to first determine the slope for FG. So y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And then this can be my x sub 1, y1, and then x sub 2, y sub 2. So plugging those numbers in, we'll have -7 minus 5 over 1 minus -4. So here on the numerator, same sign, add, keep the sign, -12. And on the denominator, that means 1 plus 4, which gives us 5. So -12 over 5 would be my slope for FG, and since they want the line parallel, we'll just use the same slope. So the slope must be -12 over 5. Then we want the slope of the line perpendicular, where perpendicular again means the slopes are opposite reciprocals. So I'm looking at the slope that I calculated here, and I'm going to change the sign and flip the fraction. So we get positive 5 over 12 for the slope of the perpendicular line.